Right, I should say right from the beginning that when we're doing a solar astronomy, we never look directly at the sun with the naked eye or any unfiltered optical instrument. So just be careful. Now, although the sun can be observed safely using pinhole projection, the best methods to obtain a large image of the sun can be obtained by using an H-alpha filter. So it's an H-alpha filter, which absorbs all sunlight apart from a very narrow range of wavelengths centered on a particular spectral line of hydrogen, which is about a wavelength of 656 nanometers. Also, you can use telescopic projection, which requires the use of a baffle card with it's a sort of piece of card with a small hole to absorb most of the solar radiation before entering the telescope. Right, so on most clear days, of course, we can see a number of sunspots on the surface, or the photosphere of the sun, not the surface of the sun, but the photosphere of the sun. And these are cooler areas of the photosphere that correspond to strong, localized magnetic fields that inhibit the upward motion of convective solar material and prevent it from reaching the photosphere. So it's a slightly cooler spot on the photosphere. And in fact, if you were to measure the temperature, you'd say the average temperature on the photosphere is about 5,800 Kelvin. Whereas if you look at the umbra, or the darkest part of the sunspot, it's about 3,800. So there's a good 2,000 Kelvin difference. If you go to the penumbra, the sort of semi-shadow around the umbra, you're back up to about 5,600. So it's only a little bit cooler than the ordinary photosphere. So by observing the apparent motion of sunspots across the solar disk, it's possible to determine the sun's rotational period at different latitudes and deduce that the sun does not rotate as a solid body. Its rotation period varies from 25 days at the solar equator to about 36 days close to the poles. So that's really quite peculiar, isn't it? Right, so the solar rotation period can be determined from recording the position of a sunspot or group of sunspots at approximately the same time every few days. So if you took like a series of pictures across a few days, you could get the rotational period, of course. And the longitudes of the sunspots on different dates can be found with an aid of transparent grid placed over the solar disk. Okay, so we have a transparent grid placed over the solar disk, and that's going to help us find the longitudes of the sunspot on different dates. Now, if the difference in longitude, that's capital L, of a sunspot occurs in time interval delta t, and that's a capital delta again, then the rotational period of the which we'll give letter t, okay, the rotational period capital T can be calculated using the formula that t divided by delta t is equal to 360 divided by delta L. And this could be repeated for different times and longitude differences from which the mean solar rotation period at a particular latitude can be calculated. Just a little bit of extra information now. So individual sunspots are relatively short-lived. Most last for a few days to a month, but the numbers and attitudes of sunspots follow a regular solar cycle of 11 years. The relative numbers and latitudes can be shown on a butterfly diagram, so called because of its resemblance to butterfly wings, and here's a picture. And the cycle begins with relatively few spots at mid-latitudes. During the next 11 years, the number appearing rises and falls, and there is a steady drift in latitude towards the solar equator. We ought to talk a little bit about what's inside the sun's interior, and the temperature in the central core of the sun is about 15 million Kelvin. And this is hot enough for thermonuclear reactions involving the fusion of hydrogen nuclei into helium, so that's H and He, hydrogen and helium, nuclei to occur. And the temperature has to be high to overcome the mutual electrostatic repulsion of the positively charged nuclei. The most common series of reactions is called the proton-proton chain. I think I've made a previous video on that, which might be worth checking out. Okay, But I'm going to put up the reaction on the screen now for you to look at. Now, at each stage in the chain, mass, and modified obviously as here as m, is lost and converted into energy, capital E, in accordance with Einstein's famous equation, E equals mc squared, where c, of course, is the speed of light. The Sun loses about 4 million tons of mass every second, but as amazing as that sounds, that's really quite insignificant compared with the Sun's total mass, which is about 2 times by 10 to the 27 tons. And immediately above the Sun's core is the radiative zone, where the energy in the form of photons, gamma radiation, is transferred in a rather random manner due to the scattering of photons by electrons onwards. So the outer 200,000 kilometers of the Sun is called the convective zone, where thermal energy is transported to the photosphere by rising convection currents of hot plasma at the base of the zone, and the temperature is about 2 million Kelvin. At the top, the 100-kilometer thick visible surface of the photosphere, the temperature is only about 5,800 Kelvin. Right, so let's now move on to the Sun's atmosphere and the solar wind. The Sun's photosphere radiates energy in the form of visible light and, to a lesser extent, infrared, ultraviolet and X radiation. The chromosphere thickness is about 2,000 kilometers and between 4,000 and 100,000 Kelvin, and the corona is about 2 million Kelvin. The photosphere thickness, I've said, is 100 kilometers. Okay. Now, above the photosphere, the solar atmosphere consists of the spherical chromosphere and the tenuous, sometimes petal-shaped corona, which extends outwards for millions of kilometers into space. The corona is only visible during a total solar eclipse, and the Earth has a magnetic field that is similar to that of the simple bar magnet. So with the solar wind, the Earth's magnetic field would resemble that of a bar magnet instead of a magnetosphere. It's somewhat more complex, as shown in the NASA graphic here to your right of the screen. Right, the slow solar wind, I'll put that slow in inverted commas, is an outflow of charged particles, mostly protons and electrons, from the Sun's corona that are ejected into space at speeds of 400 kilometers a second. There is also a fast solar wind emitted from coronal holes and gusts of radiation associated with the coronal mass ejections and solar flares. The solar wind is responsible for aurora and the creation, direction and visibility of cometary tails. In addition, it can trigger worldwide geomagnetic storms that cause overloading of power lines and add unwanted noise to radio transmissions, affect the electronic components of instruments and orbiting satellites, and add to the radiation risk to astronauts and air passengers. The Earth-Sun space environment is a fascinating subject in its own right, and there's a few websites that you might want to check out on your own. So one is called the www.spaceweather.com, and the other one is SunTrek website. You might want to check it out. So it's www.suntrek.org. Okay. And of course, I think the one thing I haven't mentioned at all in this, which is quite relevant, just finish off, is the Van Allen belts are two donut-shaped rings of charged particles trapped in the Earth's magnetic field, and the inner belt has an altitude of about 0.1 to and 1.5 Earth radii. It's about 1,500 kilometers to 10,000, and maintains mainly protons. The outer belt has an altitude between 3 and 10 Earth radii, that's 15,000 to 65,000 kilometers, and contains many electrons.